I will talk about low-degree analysis of planted random subgraphs. So we all know secret sharing, right? So Shamir taught us how to share. So if you have Alice, Bob, Charlie, and Dave, and you want any pair of them to reconstruct, you shoot a line through the secret, and then you give the shares. And, this works very well. You never ask what else you can do. But luckily, Abram, Beimel, Ishai, Kushklevitz, and Narayan asked this exact question at the last TCC, and they gave a beautiful alternative way, another way to share. So how do they share? Well, they start with a random graph, and what they do with this random graph is that they plant a small clique and a small independent set inside it at random. Okay? And then they publish it. This is some public information that they give to everyone. And what they do is suppose that the dealer wants to share a 0. So what the dealer is going to do is he is going to give, the parties there are k parties in the scheme, so there is a party associated to each vertex in the clique and each vertex in the independent set. So suppose they want to share a 0, so what the dealer is going to give is he's going to give a vertex, the identity of the vertex in this graph, to each of the participants in the independent set. So Alice will be assigned her vertex here, Bob will be assigned this vertex here, and so on. So then Alice and Bob get together to reconstruct. So what do? Well, they look up the identity of their vertex, and they look up this public graph, like it's public information, and they just output the identity of an edge. If there is no edge, they will reconstruct to 0. If there is an edge, they will reconstruct to 1. So this is, it's a really beautiful idea. And one reason why it's interesting is because now you can start asking questions as to, well, how good is it? How efficient it is? And it turns out, right, so if I have a graph of n vertices, and I can plant a clique of size about square root of n and an independent set of size about square root of n, and yet presumably give out no information about what these are. So it's plausible that any individual participant in this scheme doesn't really know whether he's looking at the vertex in here or a vertex in here. Okay, so there is some argument to be made that this is secure. And the technology we use is the low-degree method. And so why is it useful? The reason it's useful and interesting is because the share size, so to communicate the share, I just need to give a vertex in the graph to each party. And if I have a graph, it should be 2 log k, not 2 log n. If I have a graph of n vertices, I can communicate the vertex with log n bits of information. And k is about square root of n, so this would be 2 log k bits of information. So this should be a 2 log k over here. And this comes tantalizingly close to Shamir, where in Shamir we can do the same with about log k bits of information. So the natural question that arises is, can we do even better? Can we close this gap between 2 log k and log k? And the really interesting question is, can we go even below log k? Okay, so I'll try to come back this to the end. And here is one suggestion, again, from the same work, where they kind of give idea about how you can lose these extra log k bits. So instead of planting a clique and an independent set, we're going to change the setup slightly, and it affects the definition a little bit, but let's not worry about it. This is what the dealer is going to do. The dealer is going to start with a random small graph H on k vertices. And he's going to publish this graph. And now, if he wants to share a 0, he's going to plant this random graph into a large host random graph G. So all the edges of G outside this H are random, and this copy of H is induced on some random subset of vertices of G. And if he wants to share a 1, then he does the same, but he plants the complement of H instead. And reconstruction is exactly the same as before, well, almost the same as before. So what do Alice and Bob do? Alice and Bob, each party gets a vertex in the host graph. The vertices in this planted graph are already identified with Alice, Bob, Charlie, and Dave. So what Alice and Bob do is they look at the vertex they get here. So here, maybe Alice gets this vertex and Bob gets this vertex. And they compare them to what they get in H. And then they just XOR the 2 edges, right? So we know that the way that these things are set up, right, when we overlay these 2 graphs, they will also always XOR to 1 here, and they will always XOR the 0 here. What do we gain? Well, what we gain is that now we're planting a random subgraph in a graph. And conceivably, and conceivably we might be able to plant a larger random subgraph than we can do for a clique. And that's going to be the main question of interest. But before we go there, let's state sort of what we need, or at least what, it's not sufficient, but sort of what we want to have for this construction to be secure. Well, we would want to say that when an Alice in this case and an Alice in this case cannot tell the difference, right? And the way that we might conceivably argue about it is we can say that somehow both of these distributions are indistinguishable from some model distribution. And what is this model distribution? So the model distribution is a distribution in which this planted subgraph and the large graph are completely independent of one another. And this is the planted random subgraph conjecture from their work. It says that if I take a small graph and I plant it into a large graph, everything is random, right? It's computationally indistinguishable from taking a small graph and a completely independent large graph. So in some sense, these two are pseudo-independent of one another. They look like two independent copies that have no correlation to one another. Okay? And now you start asking the question, well, how large can you make this graph H to make this be true? And they conjecture that you can make this H to be almost as large as G, the number of vertices K to be almost as large as N. And now I want to give you some intuition about why you might want to expect that. And the intuition comes precisely from this kind of reasoning that you do when you do low-degree calculations. So you can think about it this way, right? I have a random graph, and now I plant a clique inside it. How would I distinguish these two? Well, I would distinguish by counting edges. Well, to be able to distinguish with good advantage, I need to have a large discrepancy in the number of edges here and the number of edges here. What is the discrepancy going to be? Well, we did the calculation yesterday, if you're at my talk. Here we have about theta of n discrepancy for a graph of n vertices. This is the standard deviation in number of edges. And here we add another something like k squared edges. So as long as k squared is bigger than n, it allows us to distinguish between the two. So the best security we can hope to get is for k being as large as square root of n. And now comes the interesting part, is that now if I plant a random subgraph instead of a clique, a random subgraph is almost balanced, right? It's going to have about as many edges as non-edges, right? And the distinguisher knows which are the edges and which are the non-edges, so he knows whether to look for an excess of edges or an excess of non-edges if he is counting edges. But the best that he can do is get an advantage of square root of the number of edges in the planted subgraph, which would be order of k instead of order of k squared. Okay, so that's the intuition. And our main result is that we confirm this intuition like in the framework of low-degree analysis. So we show that if the distinguisher is a low-degree polynomial in this low-degree framework, then indeed G is pseudo-random given H up to error about k over n, which is what the error would be for the edge counting distinguisher. So in some sense, it's that the edge counting distinguisher is close to being optimal within the framework of low-degree algorithm, and this works all the way up to degree a little bit less than log squared n, which is what you would expect. So it's for the same reasons that you get log squared n for the clique. There is this fudge factor of log n that's kind of an artifact of the method, but that's it. Okay, so this is the main result. And now I want to tell you a bit about what else is going on here. So I really want to tell you more about why this is interesting and how it applies to cryptography. So first of all, this is not exactly what you need, because it turns out that when you apply this to secret sharing, there is a bit more information revealed. Alice doesn't only see the graph, the public graph, but she also sees the correspondence between her vertex in the planted graph and her vertex in the public graph. So there is some leakage about this graph revealed that Alice's vertex here maps to her vertex here. That's her secret, that's her share. So that's revealed to her. And so now you actually need to say, is it secure even if you reveal this information? And that's not something that you can argue using standard cryptographic techniques like conditioning, because the distinguishing advantage here is quite high. But it works with the low-degree method, and we can show that it's even if you have the leakage, it's still secure. Okay, so we get this, so now we get ambitious, we want to do more. So what more can you do? Well, you can say, now let's consider other kinds of access structures where maybe not every pair of parties can reconstruct, but I give you a graph and only the parties that are connected by edges in this graph can reconstruct. Okay? And it works, like the same construction works. Everything is from their work. But now you can ask more about secrecy. You can say, well, now, what if Alice and Dave get together? They should still not be able to get information. What if Alice, Dave, and Fred get together? They should still not be able to get information. So you can think of kind of any independent set as being a coalition that tries to, extract information they're not supposed to. And you can ask, is it secure? And yes, it turns out it's secure as long as the coalition is not very large. And somehow the error, the security error that you get becomes larger with the size of the coalition, which is what you expect. And indeed, if the coalitions start having size something like log n, then it turns out that you can attack the construction and you can reconstruct the graph. So this is kind of the best possible, at least for this kind of construction. Okay, so that's about, the secrecy, like the parties that you're secret against. Now you can go in the other direction. You can say, well, maybe you're not happy with graph. This is what's called forbidden graph secret sharing, which only allows reconstruction by pairs. What if I want my, my minimum reconstruction sets to be like triples or some large subsets? So you have something called the hypergraph access structure where the minimal sets are like some hyperedges of larger size. And is it still secure? Yes, it is secure. And what changes here is that now the degree of the distinguisher goes down. Now it turns out that to distinguish, you have to look, well, kind of for a clique or for something in this subgraph that consists only of hyperedges. And this kind of objects exists in a random graph with a much smaller size. So you get some loss in the degree. It's not too important, but this is the parameter that you would expect to get based on like how you would distinguish this with a slightly high degree polynomial. And indeed, the low degree method tells you that this is optimal. Okay, so now that these are sort of the main results, so now I want to tell you, well, how did we get this result and why is it not in their paper? And the reason is that there is a simple trick that they didn't know because they didn't talk to the physicists, and this trick is the replica calculation. Okay, so how does the replica calculation work? So if you were at my talk yesterday, you saw that the low degree ratio, like if I project it to the space of degree d polynomial, is some kind of sum of squares of Fourier coefficients. Now what we're going to look at is not the low degree ratio, but the average low degree ratio averaged over the subgraph H that we're planting. And this is where we gain, when we're averaging over this subgraph H that we get. And now we can use the replica, and replica method says that if I have an expectation of a square, I create two replicas of the graph G. I create one G and YG prime, condition on them having the same subgraph H planted. But everything else is independent. They're planted in very different places, and so on. So then what you end up having to calculate when you do the replica calculation is the sum of expectations of, I have now some edges where I probe the graph, and I want to know what is the parity with respect to set when edges are represented by plus minus 1 in the graph G. Here the variables are the adjacency matrix G, and in G prime. When you do this calculation for clique, let's say that this set S has size 1, so you just have a single edge. It turns out that this is something we saw yesterday. This doesn't vanish exactly when this edge is covered by both the clique in G and the clique in G prime. So it has probability about k over n squared. And the point is that here, if it's just covered, things might still cancel out. Because maybe it's covered by edge 1, 2 in one graph, and it's covered by edge 3, 4 in the other graph. So here you have G1, 2, here you have G prime 3, 4, and those are completely independent. They're unrelated to H. Okay? So there is an extra condition that needs to be satisfied for things to cancel out, which is that when you embed the subgraph both into G and this H, it has to be a double cover. Every edge in S has to be covered once in G and once in H. Okay, so that's kind of the short story about where the gain comes. And once you have this, then it's just doing a difficult calculation, and that was the job of my co-authors, Chris Jones and Ilya Zadig. So they pulled off this to perfection. Okay, so there is one other application in the paper of Abram et al., which I'm not going to tell you about. I'm just going to tell you about sort of what you need to reason about. It's something called private simultaneous messages for random functions. And the point there is that the leakage that you get is actually not a single vertex, not a single edge, it's some subgraph. And in the secret sharing application, the subgraph that you leak is independent of the subgraph H. In this application, the subgraph that you leak might itself depend on H. And this creates more complications in the calculation, and the way that you deal it with technically is instead of putting a 2 here, you put a 4 or some 16, some large power, and then everything works out. Okay? So that's the short story. Now I want to tell you, for the last 30 seconds that I have, that all I told you about is actually not necessary, because in the paper of Abram et al., they have another very beautiful way where they explain not a better, but the best way to share. Okay, and what's the best way to share? The best way to share is that in my host graph, I have some class of vertices associated to each party, and then what I do, I either plant a random clique and a random independent set, but which is spread out across the parties. So this would be the clique, and this would be the independent set. And the advantage of this is that now, to give Alice's share, you don't have to worry about this part of the graph at all. You just need to communicate one of these bits over here, right? One of these vertices over here. And this is a beautiful problem, and they prove in their paper that's in fact a complete problem for 2 out of n secret sharing. And using this, like from the planted clique and planted clique conjecture, you can get the secret sharing scheme which has essentially the same parameter as 2 out of n Shamir. The share size is very close to log n. You can make it as close as you want. And a tantalizing question they leave open is whether you can go below log n, which we don't know how to rule out. So I will leave it at that.
Any questions?
So I'm not sure I understand. Yeah. So I'm not sure I understand.
No, that's not a good. That's not a good sign if you don't understand.
No, the value of k using these random subgraphs. Why can't you choose any value of k? So consider the following 2 distributions for an n and k. So you first choose a random graph with k nodes. And then you plant it into a larger graph with n nodes by picking n minus k new nodes and then adding random connections to the one that you already have. Or you take a random graph with n nodes and then you select a random subset of size k and you say that, oh, that's the size k subgraph. And to me, it looks that these are exactly the same distribution for any value of k.
Yeah, they're the same distributions. But the point is the correlation between H and G. Like, I give you both the subgraph that I planted, so you can generate it like that. I take the random graph, I take the random subgraph, and I tell you this subgraph is somewhere in there. So I give you both.
Oh, okay, okay.
I tell you where it is.
Okay,
it's the
so
distribution of H and G that you're looking at.
Okay, so once you pick the random n-node graph, selecting a random subset of size k will not be uniformly random if k is large enough, which is clearly, yeah.
No, it is, so by itself it's random.
By itself, but
no.
Yeah.
So actually, statistically, you're unlikely to see it in a random graph, right? That's the point. So if I look H and G independent, then it's not going to look like that.
Thank you.